So we started the whole dynamical system in complex point, complex inputs and also the complex output. We presented a little problem, and the last thing we talked about yesterday was about, okay, how do we then one actually graph a complex function? And that presented a lot of problems. First, because in real number system, given a function, you have x your input, y your output. Matches up with the x-axis and the y-axis. You have a point that by varying your inputs, you can vary your outputs of a graph. Right? So simple, my favorite mother function, x squared is over real is just a parabola, right? No problem. But when you transfer that same function to a complex plane, where the input is a plus bi and output is also a c plus bi form, you run into a problem. How are you going to plot a point? It requires four variables in C. So it's A, B, and C, D. And we saw an example of that utilizing 3 plus with and plus. Remember this and by different shades of colors you represent that. So I'm not going to go in detail, but think about that. Yeah. But we are not graphing regular functions, are we? We are graphing the dynamical system. And we are coming up with our rule as to how to plot a point. Now, if you remember, yesterday, given all these orbits, orbit of different seeds of the function x squared, c squared, because c is a complex number written in this form. We have observed that some of these orbits tend to either a constant function, a constant 0 or 1, or they tend to either positive or negative infinity. And you guys came up to the board and drew the point. Now, let me iterate this point. When you came up and plotted the point, what was the point that you plotted? Initial seed is what you plotted, and depending on how the orbit behaves of that seed, you drew that point with red or black. Which is obviously I just have to show the colors. Black was 1 that tend towards either 0 or 1. Red was when it tends toward infinity, using your calculator, correct? And we talked about, Jay, I'm a little confused because if you do orbit of C, eventually you get an S. It seems like the orbit, when it tends to infinity, you have A plus BI form. So how do I know, in real function, you know there's only one number, right? You get the y value as a one number, and if that y value is what infinity, you know it is infinity. But in complex, you get your output as A plus BI form. How do I know, whether that number tends to positive or infinity? Do both A and B has to increase or decrease to negative or positive infinity? Or is either one going to be a big number fine, or what's the case? Do you see the dilemma here, right? So what do we say? We say if that number is what? Going away from the origin, which numerically means what? Either A or B, or both. Then we will say that orbit tends toward infinity. Does that make sense? Okay. And if it does, we will pick that seed and plot that seed on this complex plane as either black or red, depending on how the orbit behaves. Right? And yesterday we saw that. Now, how many possible seeds are there? There are infinitely many, right? For the fact that the domain of this particular complex function x squared is all complex numbers. Just like all real for a real x squared function, right? So How many did we test? We tested 8 C's. We tested 8 points out of infinity to understand this. Obviously, that's a limited number of information to do that. But if you do that enough, you will get some sort of picture that looks like this. And that's a unit circle. Yeah. It's black because every single point on this curve will tend towards what constant? Not 0 or 1. Every single point on this curve will tend towards which constant? 1. How do I know that? Because if I turn any point on this curve into polar system, which will not be a plus bi form, but r comma theta, then r will always be what? 1. So, if, for example, my seed, -1, -1 is right here. What is the polar conversion of that -1? 1 comma pi. Correct? That's my seed. So, what do I do with that seed? I square that. When I square that, what do I get? 1 comma 2 pi. When I square that, I get 1 comma 4 pi, and so forth, correct? What does that mean? We'll go back to 1. 1 pi, 2 pi, 2 pi, 4 pi, right? It tends to 1. And any point on this circle will tend to 1 because radius is 1. Yeah. Yes. Because I said you only do red if it tends, it goes away to infinity. So every single point of that. Now this particular set of points. Now how many points are on this set? Obviously infinity. What will be the cardinality of this particular set? C. This particular set is called the Julia set. Not Julia. Someone's lover's name, Julie? The mathematician. But Julia is not the last first name. It's the last. Someone's last name. It's a mathematician. During World War I. And he's the one who came up with the whole dynamic system idea as to given a seed, put it through the function, output, use that output as a new input, put it through the function, and on and on and so forth. But obviously his work had to stop. Why do you think it really case? Because of this particular case, the infinitely many what? Iterations you need to perform to come up with one possible graph of x squared over complex. You see, that's why it limited it from computational sake. It's not fun just sitting there doing the same calculation over and over to try to come up with a one. If I had a computer, it would be that like. That's why sometimes you're better lucky than good if you're born in the right time. The technology available is and even our calculator can do this. You are actually going to program it. Or it will help you program it. Not only to understand the concept, but as to how to do this. I mean, how would you do this? Well, I mean, first you will definitely do a loop. If let's say you do about 20 loops. Given a C, you go through a function, blah 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 blah. If either one A or B approaches, let's say, bigger than 10,000 or something, then whatever that point is on the window, I'm gonna have a pixel on or off to represent that black or whatever is not. Does that make sense? So I'll do, let's say, on a, the graphic calculator are done by pixels, right? Which could be located by x comma y. So given that seed, you could definitely put that point pixel on and off. If it does not reach, if it stays less than some odd number that you can come up with, then it will be pixel on. If it reaches beyond some number, then you can pixel off. So you're gonna get that circle. Which is not a crazy thing to do, isn't it? Something you could do. Anyway, so what is this ring called? Julius. Why? Because it tend towards 1. Right? Now, what about stuff inside? All the points inside. If you look at the orbit behavior, will the orbit approach 0? It does, right? Eventually. Right? Some orbits might get to 0 a little bit faster than others, but it will all eventually approach 0. So that has to be shaded with black. Right? And everything else is red. Should I do that? Now, let me take out. Oh, I can't take it out. Right, let's pretend. Here is that Julia set right there, correct? This is a Julia set. But what do we call this? We call that a filled Julia set. It's different. Julia set is the boundary of the black area. And what's inside the black area is called the filled Julia set. Let me formally define the two. So, for the rest of this chapter topic, we are going to exclusively study complex function of the form x squared plus c. Now, is that the only quadratic complex function? You could definitely have complete complex function of degree 2 this way. But if you want to dive into it and do it on your own, you could. But we're just going to study z squared plus c. Does that make sense? Where c is complex number. It's not defined. Well, we did for the previous do not question. What was the c value of the do not question, boys and girls? 0. Make sense? Okay. C squared, squaring function. This is a crazy motherfucker. Okay, so filled Julia set. So given the quadratic equation z squared plus c in complex, the filled Julia set of q sub c, for our case it was 0, q sub 0, consists of all points whose orbits are bounded under q sub c, meaning it tends toward either 0 or 0. The Julia set, not the filled Julia set, but just the Julia set, is the boundary of the filled Julia set. Does that make sense? So it's a definition between a circle or the ring versus a disk, which does not include the ring. Definition. Now, going back, in order to fully understand z squared, our previous question for the do now, how many points, how many c's do you need to test? Infinitely many. And for each infinitely many c's you chose, how many iterations do you need to do? Infinitely many. Right? So create 1 point on z squared function, you need to do infinitely many iterations. And there are infinitely many points that require infinitely many iterations. Are you ready? Now, I'm adding infinitely many other possibilities of c. which will produce infinitely many graphs. There's layers to this. You know what I'm talking about? Alright? So, we just dealt with z squared plus 0 plus 0r, which is this is 0. Let's do z squared plus minus 1. My c value now is negative 1. Okay, so let's review. When c equals 0, which was a do not question, right? It's just z squared. A plus bi could be written in terms of r comma theta. And given that, when r is less than 1, it tends to 0. Greater than 1, it tends to positive infinity. Or when it's equal to 1, it's on the ring. Okay? Makes sense, right? So now let me change the c value. No, not yet. Here's a graph of when z is equal to 0. Does this look a little mysterious? I think it's because of color. But can someone observe as look at this? Just look at it and tell me what you think. Let's say something obvious. Something obvious first. Don't give me try to indicate. Say that one more time. As the unbounded points, which are not in the field Julia set, right? Because the points that are in the field Julia set and on the Julia set, they are bounded. So he's talking about points that are not in the circle. So points that are not close to this one, but rather points that are away from the circle. Makes sense, right? Well, this point right here, the corner right here, will that point, how many iterations will that point take to reach a big number? Not that many. Well, if I were to, what's not that many? That could be relative, right? But if I compare that number of iterations to reach a big number versus numbers that are very close to the circle, you know it will take less of it. Meaning, on the other hand, the points that are close to the circle, it will take a lot more iterations to reach a big number. And they made a distinction between those two seeds by color of, by the shades. Does that make sense? All right. So darker the color, it approaches infinity faster. Lighter the color, it reaches infinity slower. But eventually it will reach it. Make sense? And as I said, even inside the filled Julia set, some of the seeds will take longer to get to 0. Which they didn't choose to differentiate that color because they just want to stay as a filled Julia set. Now, so let's vary the equation. Let's try to find the filled Julia set when c is -1. What kind of function is that? How would you write that function? That is of q of z is equal to z squared minus 1. That's what it means. Now, for this particular c value, how many seeds do we need to test and observe the orbit? Once again, infinitely many, which will create infinitely many points according to our simple definition of if that orbit tends to infinity, it will be red. If the orbit is bounded, it will be black. Do you think when c is -1, the Julia set the graph will be same as when c was equal to 0? No? Okay. I don't know. Well, how do we test? We better test some of the different seeds. Now, let me try to generalize something. Given the function q of z, which is equal to z squared plus c, my z, the input, is a plus dl, correct? Why am I doing this? Because I'm trying to come up with a generalization of this iteration so that I could put it in the calculator and come up with the output in one formula. Do you know what I'm trying to do? What will be c equal to? C plus di. And what am I doing with these inputs? And define c. I will z square that, which will give us a squared minus b squared plus 2ab I. And what am I doing to that? I'm adding c, which is c plus di. So let me write that as a squared minus b squared. What? Plus c, the real part of your output, and plus parentheses 2ab plus di, the imaginary part of the output. Now this is a formula that I use to iterate over and over. You don't have to try to do. Now, Mr. Che, why didn't we convert the seed into polar before to simply come up with whether it tends to infinity or not? Why can't we do the same thing here, Mr. Chen? Meaning, pick your seed, whatever seed might be. When I change the value of c from negative 0 to negative 1, does that change anything in terms of doing the same polar conversion? Yes. Exactly. Every time there isn't, before, all we have to do is what? Square the seed, right? Well, what do we have now? After you square, we have to subtract a constant, which then will be a different number that you're squaring over and over again. So you cannot apply the r greater than 1, less than 1, or equal to 1 right away on that. Do you know what I'm talking about? Okay? Because of that different process, you can't do that conversion. It was nice. Right? Easy enough. But I could come up with that. Now, what would I do with this? Well, just like I used Excel before over the wheel, we had to use a phase portrait. Do you remember that phase portrait? With the arrows pointing at all of the places, right? I used the Excel to come up with that over the point decimal point 1. So how would I do this also? Nice. Okay, am I losing you guys? Are we okay? Hopefully you watched the video about 1,000 times. Or at least the amount of iterations that you need to do for each seed. And then watch it again over for every seed. And then do all values of possible seeds. What's the iteration? Or just start asking. No, that's probably the best way to begin understanding. By asking obvious and simple questions to establish your foundation. So here we go. Here we go. Let me switch up. Here is my diagnosis of the function c squared. That's my dynamical function. Here is my z value. There are infinitely many z values you could choose. I choose to use 0.5, 0.5. So that's my z value. Let's see what it is. So what is this? That will be my z value, which has a real order. Here's my C. So C value. I just need to test it. Okay. Here's my, so what's my first iteration? I need to square 45 plus 45i, correct? And then subtract 1. Whatever that is, I need to square that again. And then subtract 1. Square that. So, here's my C. So how do I get my new output? The real part of the output and the imaginary part of the output. That's why I had to do the following. There is what I have. This is a formula that will give me the real part of the output. Here's my formula for the imaginary part of the output. Instead of D, what would I have? 0. Instead of C, I would have. So, here's my formula. B squared, I wrote it in column A. So if I actually take this, A squared minus B squared plus C. I have those dollar signs there because it will never change. It's a constant. Or you could just drag and drop the whole thing, and every time C is negative 1 is 0. It doesn't matter. And then, how do I calculate the imaginary part of this? 2 times, 8 times, 8. Correct? Now, Mr. J, why don't you have the B part? Because my D is 0. But if I want to, because I might actually want to change my C. And my C value later, because I can put it in if I want to. Maybe definitely have 1. Plus D, which I will click. Did it change anything? And then you drag, and you get this. What do you see? You see either A or B, the output is reaching a big number. Right? E to the positive 2 equal is a big number. Okay? And it's like graph. That's not a graph, but just like the area. What does this tell me? It starts from here, and it's going outward this way. It's going away from the origin. So it's definitely, what is it doing? It's definitely what? Increasing to infinity. Now, what does that mean? Then that point will be colored with red. What if I pick different C value? 2 and negative 3. Okay, why are we dealing with C values that are relatively small? Why am I picking C value 20? They are not interesting. Why aren't they interesting? Because big number squared is going to be a big number. It's only interesting when it is between 1 and 0, or a little bit over 1, right? So that's why I'm only picking numbers that are small. So, how do you interpret this? What is happening? We start at 0.2 and negative 0.4. then it goes all different places, and eventually what happens now, after about iteration, it reaches what? It says negative 2, I know. That's because it estimates. The orbit of point 2 minus point 4 I tends towards 0 on the cube and c equals negative 1. Thus, like the pace in the physics. So it's not really. It almost looks periodic. 0, 0, and negative 1, 0. But that's okay. That's still part of the as long as it doesn't fly. Now, you better pay attention because you need to listen at home. So you better know that formula that I derived right there, which is quite easy to do, obviously. Right? You better know how to do this in Excel. This is great. And over this 0.2 to the time and negative 0.4. It's still the C is negative because C is negative 4. What in the world? Do you see any sort of pattern? What? Right there? No, let's go to infinity, so I'm good. Alright? Up here is bounded because it doesn't approach infinity. It looks like either it's going to be what? Like complete chaos, there's no pattern. Or, if I did enough iterations, it looks like there will be some sort of eventual periodic, or it gets fixed. I don't know, but it looks like there's not going to be infinity. And you see how computer programming will help us to such. You need enough of this. And if the same points happen over and over again, you know, and the graph is so here's another example. Yes. This example. First of all, I changed the C value, so we are talking about different function altogether. But for the illustration's sake, look at this. It's by 0, 0. Oh, that is probably the most important C of this every different function. Is that one more? 0, 0. The first order, first C. So, as I iterate this over and over again, what do you observe? Isn't it nice? Look at this graph right here. Isn't that beautiful? That triangle has a meaning. Doesn't matter. Because we talk about, we want to know not the beginning behavior, the end behavior. End behavior of the order. It could be that it's overshadowed because it seems like there are a couple more points down here. But you see in blocks of threes, same numbers appear over and over again. Where at least it's getting closer to those numbers. 5, 6, 5, 6, 5, 6, 5, 6. Negative 0.1, negative 0.01, negative 0.01. And then 0.74, 0.74, 0.74. Looks like this is, it looks like eventually it will be a periodic distribution. So you would just focus. So here's what I want to say. If I said as your first C for every different C value, which will be a different function, you try 0, 0. And if that 0, 0 is bounded, that C will be a member of a new set called Mandelbrot set, which is not Judas set, nor it could be part. It will obviously be part of it, but we'll get to that. Get enough pushing. Try the homework question 1 and 2 that I assigned yesterday. Finish that up.